Welcome to the deep dive. Today, we're tackling a topic that's absolutely fundamental to modern life, yet, often unseen: how we protect ourselves from electric shock and electrical fires.
Mm,
We've got a really detailed guide with us, built on international IEC standards. Think of this as your express route to understanding electrical safety, what truly matters, without getting lost in the weeds.
right.
We're aiming for those aha moments, the ones that make complex stuff suddenly click.
Exactly.
Yeah.
And you've brought a wealth of information here. Our goal is to really pull out the crucial principles of electrical safety for everyone listening.
Okay.
We want to paint a clear picture of how we're shielded from harm, especially, when things don't go quite according to plan in an electrical system.
Okay, so let's start with the main threat: electric shock. It's not just a little tingle, is it? What's the real danger here?
Absolutely not. Electric shock is basically what happens when an electric current interferes with your body's normal functions. And this can have really severe consequences for your muscles, your heart, even your breathing. And, of course, it can cause burns.
Right.
The severity isn't just about feeling a shock. It really depends on the amount of current, the path it takes through your body, and, crucially, how long it lasts.
So is there like a scale for this? A way to really grasp how dangerous it can be?
Yes, there is. There's a sort of danger scale laid out in IEC 604799. It divides the effects of AC current on the body into 4 zones.
4 zones.
Yeah, based on current strength and time. Zone 1 is usually imperceptible. You wouldn't even notice it.
Okay.
Zone 2 is where you start to feel it, definite sensation.
All right.
Zone 3 can cause reversible things like muscle contractions you can't control. But Zone 4, that's where it gets truly serious.
Zone 4 sounds bad.
It is. That's where you have the increasing possibility of irreversible effects, including heart fibrillation.
Heart fibrillation. That sounds, well, terrifyingly serious.
It really is. And here's a key takeaway, a really important one. If a current as small as 30 milliamperes, that's tiny, really tiny, flows near your heart and isn't interrupted almost instantly,
Yeah.
it can be fatal.
Wow. 30 milliamps.
It highlights just how critical that rapid protection is.
Yeah.
And it's also worth remembering that electrical fires, which we should definitely talk about later,
We will.
can start from things like overloaded circuits, short circuits, and even tiny electrical sparks called arcs.
Okay, so protection is clearly vital. What's the most basic rule we should know, the fundamental idea?
The fundamental principle, according to IEC 61140, is this. Any part of an electrical system that's normally live and could be dangerous,
Right.
it just shall not be accessible.
Right. Keep away from the live bits.
Exactly. And any parts that you can touch, accessible conductive parts, they shall not become hazardous,
Well-
even if something goes wrong.
Okay, that makes sense.
And this applies both in normal everyday use and if a single fault condition occurs.
That makes perfect sense. Keep the zap zones off limits and make sure anything we touch stays safe. How do we actually do that?
Well, there are several core methods. One is automatic disconnection of the power supply when a fault is detected.
Like a circuit breaker tripping?
Precisely, flipping almost instantly.
Yeah.
Another is using what's called Class 2 insulation. Think of it like having a double layer of protection around the live parts.
Okay, double insulation.
Preventing contact through physical barriers or simply by keeping things out of arm's reach is also key in some situations.
Makes sense.
Then there's something called equipotential bonding. That's basically making sure all the metal parts you could potentially touch are at the same electrical level.
So no voltage difference between them?
Exactly, to prevent shocks. And finally, using isolating transformers can create electrically separate, much safer circuits.
So it's not just one silver bullet, it's a combination of these defenses. Now, the guide you shared talks about different types of protection. Can you break that down for us a bit? Certainly. We can broadly think about two main scenarios. There's directly touching a live part. We call that direct contact.
Okay, touching the wire itself.
Yes. And then there's touching something, maybe a metal casing, that has become live because of a fault that's indirect contact.
Right, the sneaky danger.
Exactly. So, to deal with these, we have two main categories of protection: basic protection, which stops you from touching live parts in the first place,
Okay,
and fault protection, which kicks in if a fault makes something normally safe become hazardous.
let's tackle basic protection first then. How do we stop ourselves from touching those live wires under normal conditions? What are the methods?
There are a few key ways. The most straightforward is making sure all live parts are properly insulated.
Right, covered up.
Yes, with materials that meet specific safety standards. And it's important to know something simple like paint or lacquer That's not enough.
Good point. Not just any coating.
Definitely not. Another very common method is using barriers or enclosures. You see these everywhere. In electrical panels, control cabinets, equipment housings. Yeah, the boxes things come in.
Exactly. And to really prevent direct contact, these need to have a protection level of at least IP2X or IPXXB.
Ah, IP ratings. I've seen those. They tell you how well something is protected against, like fingers in water.
That's it, precisely. Think of the 2 in IP2X as meaning you can't easily stick a finger or something finger-sized in there and touch something live.
Okay, good barrier. What about openings in those boxes, like doors or panels?
Right. Any openings like that should generally only be openable with a tool or a key.
Makes sense. Needs deliberate action.
Or they should only be openable after the power inside is completely switched off. Alternatively, sometimes there's an automatic safety shutter, like a screen, that closes when you open it and can only be removed with a tool.
Gotcha. And the metal parts.
Oh, absolutely crucial.
Yeah.
Any metal parts of these enclosures must be connected to the protective earthing conductor of the electrical system. Very important.
That makes sense for, contained equipment.
Hmm.
What about situations where things aren't necessarily in a box, maybe in specific industrial areas?
Good question. In areas that are only accessible to skilled or trained people, electricians, engineers, folks like that protection might be achieved differently.
How so?
You might use obstacles to physically keep people away from live parts, or simply by placing those live parts far enough out of arm's reach.
So distance as protection.
Yes, but again, only in controlled environments for skilled personnel. This is covered in detail in IEC 603-64441. Lastly, for very specific situations like really low power circuits,
Yeah.
using extra low voltage or ELV, or maybe limiting the energy of any potential discharge, can serve as a basic protection measure.
Okay, that covers how we avoid directly touching live stuff. Makes sense. Now, what about fault protection? What happens when, say, a motor casing becomes live because of an internal fault?
Right, that's exactly what fault protection is designed to handle. There are 2 main elements to it.
Two elements, okay.
First, you need to connect all those exposed metal parts, the motor casing in your example, to the earth. And you create a network that bonds them all together electrically.
Earthing and bonding. Got it.
Your guide covers this in Chapter G, Section 6. The second element is automatic disconnection of the power supply to the part where the fault has occurred.
Cutting the power fast.
Exactly. And it has to happen fast enough to keep the touch voltage, that's the voltage you might feel, if you touch the faulty part, we call it UC, within safe limits for the duration of the fault. Figure F6 in the guide illustrates this concept quite well.
Touch voltage UC. So that's the potential shock you might get if you touch that faulty casing.
Precisely. And as figure F7 shows, there's a direct relationship. The higher that potential touch voltage, the quicker the power needs to be cut off to prevent harm.
Makes sense. Is there a limit?
Yes. The generally accepted safe limit for touch voltage that you could theoretically withstand indefinitely is 50 volts AC.
50 volts AC.
Okay, for DC, it's a bit higher, 120 volts.
Yeah.
Figure F7 also gives us the theoretical maximum disconnection times for different types of electrical systems. You mentioned TN and TT systems earlier.
Yeah, we'll get to those.
Right. It shows the times based on the normal voltage to earth, which we call UO. For instance, in a common 230-volt AC system, the disconnection for things like socket outlets should happen in just a fraction of a second, like 0.4 seconds.
Wow, that's really fast. Okay, so TT and TN systems. We'll definitely need to unpack what those mean.
Yes, absolutely.
Yeah.
We will. But the crucial point here for fault protection is that the system has to be set up so that a fault triggers a rapid automatic disconnection of the power.
And that usually involves?
It usually relies on those exposed metal parts being properly connected to earth. That provides the path for the fault current to flow and trigger the protective device.
Okay. Now, the guide also mentions additional protection using something called high-sensitivity RCDs. That sounds like a really important backup, like a safety net.
It is indeed a very important safety net. While the basic and fault protection measures we've discussed are absolutely essential, real-world experience tells us they're not, well, foolproof.
Things can go wrong.
Things can go wrong. Insulation can degrade over time, accidents happen, maybe maintenance hasn't been kept up, people can be careless, wires get damaged.
Right, wear and tear.
Exactly. Or even accidental contact in unexpected situations, like involving water. So high-sensitivity residual current devices, or RCDs, provide a critical extra layer of safety in these situations.
Okay, RCDs, extra layer.
Think of them as a very, very sensitive alarm system for electrical faults that involve current leaking to Earth.
How do these RCDs actually work? What makes them so sensitive compared to, say, a normal circuit breaker?
Well, they're incredibly fast-acting switches. What they do is detect even very small amounts of electrical current leaking away to Earth.
Leaking away, how?
Well, that leakage could be going through a person, unfortunately, or an animal, or maybe just through damaged insulation or a fault in the wiring somewhere.
Okay.
They work by constantly comparing the current flowing into a circuit with the current flowing out on the neutral wire.
Like balancing scales.
It's exactly like balancing scales. In a healthy, properly functioning circuit, those currents should be perfectly identical. If there's a difference, even a tiny one,
Yeah.
it means some current is taking an unintended path. It's leaking away to Earth somewhere.
And the RCD spots that difference.
Instantly. RCDs designed specifically for protecting people are typically set to trip to switch off the power when they detect a residual current, that difference, of just 30 milliamperes.
30 mA, that sounds incredibly small.
It is tiny. And as figures F9 in your guide illustrate, they react extremely quickly, much faster than the time it would take for that small current to cause serious harm to the human body, especially fibrillation.
So a minuscule imbalance triggers this super fast trip. That's impressive.
Hmm.
Where are these high sensitivity RCDs particularly crucial? Where are they required?
According to the IEC standards, like IEC 60364, they are mandatory for circuits supplying general use power outlets, socket outlets rated up to 32 amps that are likely to be used by ordinary persons.
So basically, our regular wall sockets at home or in the office?
Pretty much, yes. They're also required for mobile equipment rated up to 32 amps that's intended for outdoor use.
Okay, outdoor equipment too.
And also for AC final circuits supplying luminaires, lighting fixtures in dwellings, in homes.
Right. So sockets, outdoor gear, and home lighting.
Yes. Now, while they might not be legally mandated everywhere else, their use is very strongly recommended because they offer such excellent protection against both direct and indirect contact.
A double benefit.
Absolutely. Some best practices even suggest limiting the number of sockets protected by a single high-sensitivity RCD, maybe to around 10, just to help pinpoint faults easier and avoid nuisance tripping.
Good tip.
And importantly, as figure F10 shows, these 30 mA RCDs work effectively with all types of earthing systems we're going to discuss: TT, TN, and IT.
Okay, perfect segue. Let's dive into those earthing systems now. First up, the TT system. What's the core idea behind that setup? How does it work?
Right, the TT system. The key thing to understand about TT is that all the exposed metal parts of the electrical installation, the casings of appliances, metal conduits, etc., are connected to their own dedicated earth electrode, right there at the installation.
Okay, the building has its own earth spike or mat.
Exactly. Now, the power supply itself, like the transformer down the street, is also earthed. But, and this is the crucial point for TT, the power supply earthing point is electrically separate from the installation's earth electrode. They aren't directly connected by a wire.
So they rely on the ground itself as the connection.
Precisely. Because of this separation, if a fault occurs, say a live wire touches a metal casing, the path for the fault current back to the source involves going through the ground twice, through the installation's earth electrode, through the general mass of earth, and then back up through the power supply's earth electrode.
That sounds like it would have quite a bit of resistance.
It generally does. The impedance of this earth fault loop is often quite high. This usually results in a fault current that's relatively low, maybe just a few amps, sometimes more, sometimes less, but often too low to reliably trip traditional overcurrent protection like fuses or standard circuit breakers quickly enough.
Okay, so fuses might not blow fast enough, or at all.
Exactly. And that's why in TT systems, residual current devices are absolutely vital for safety. They are the primary means of achieving automatic disconnection in case of an earth fault.
So the RCD is the main safety net in a TT system because the fault current might be too small for fuses or breakers.
You got it. The RCD detects that leakage current directly, regardless of the loop impedance.
What level of sensitivity are we talking about for these RCDs and TT systems? Is it always 30 mA?
Not necessarily for the main fault protection, although 30 mA RCDs are still needed for that additional protection on sockets and things we just discussed. For the main fault protection in TT, the sensitivity of the RCD, which we call I delta N, is directly related to the resistance of your installation's earth electrode, which we call RA.
Right, the resistance of that spike or mat.
Yes. The rule is that I must be no greater than 50 divided by RA in ohms. So 50 volts divided by the earth electrode resistance gives you the maximum permissible RCD trip current in amps.
Okay, 50 RA. Are there exceptions?
Yes, for certain locations considered higher risk, like temporary installations on construction sites or agricultural and horticultural locations, the requirement is even stricter. There, I need to be no more than 25 divided by RA.
So twice as sensitive, essentially.
Effectively, yes. Figure F12 in the guide gives you a nice visual idea of the maximum permitted earth electrode resistance, RA, for different standard RCD sensitivities at common voltage levels. Basically, the lower your earth resistance, the less sensitive the RCD theoretically needs to be. But using a more sensitive RCD like 300 mA or 100 mA is generally better practice and provides a wider safety margin.
Can you give us a simple example of how this works in practice, just to make it concrete?
Sure, let's imagine the power supply's earth electrode has a resistance of, say, 10 ohms, Rn, and your building's earth electrode, Ra, has a resistance of 20 ohms.
Okay, 10 ohms at the source, 20 at the building.
If a fault occurs, live wire touches an earth casing, the total loop impedance is roughly Rn plus Ra, so 30 ohms. The fault current, ID, would be the voltage to earth, say 230V, divided by that 30 ohms, which is about 7.7 amps.
7.7 amps. Is it that dangerous?
Well, the current itself might not trip a large fuse, but the touch voltage on that casing would be the fault current times your earth resistance, so 7.7 amps times 20 ohms. It's 154 volts.
Ouch. Yeah, that's definitely dangerous.
Absolutely. But now let's apply the RCD rule. Rn must be 50 Ra. So 50 20 ohms equal 2.5 amps or 2,500 milliamperes.
Okay, so the RCD needs to trip below 2.5 amps.
Right. So if you install a standard 300 nA RCD, which is much, much more sensitive than the 2.5 A maximum allowed, that 7.7 amp fault current is way above its trip threshold. It will see that imbalance instantly and trip very quickly, typically within about 30 milliseconds, cutting off the power long before that 154 volts can cause harm.
Ah, okay. That really clarifies how the RCD sensitivity ties directly into the quality of your earth connection. Lower resistance is better, but the RCD provides the guarantee.
Precisely.
Are there any other specific rules or practical things to consider with TT systems, like disconnection times?
Yes, definitely. As shown in figure F13, for most final circuits in a TT system, those circuits supplying socket outlets up to 63 amps, or fixed equipment up to 32 amps, the maximum time allowed for the power to disconnect in case of a fault is quite short.
How short?
It depends on the voltage to earth.
Yeah.
But for typical 230V systems, it's 0.2 seconds. For lower voltages, it can be slightly longer, up to 0.3 seconds. For voltages above 230V, it gets even shorter, down to 0.04 seconds.
Very quick. And other circuits?
For other types of circuits, like distribution circuits feeding subpanels, the maximum allowed time is longer, typically 1 second. It's also important to know that RCDs come in different types, as illustrated in Figure 14. There are general-purpose ones, and then there are selective types, often marked with an S.
Selective RCDs, what's special about them?
They have a built-in time delay. This is really useful for achieving selectivity or discrimination in larger installations.
Meaning
you can have, say, a slightly less sensitive, time-delayed S-type RCD protecting a whole distribution board, and then standard instantaneous RCDs on the final circuits fed from that board. If a fault occurs on a final circuit, only the downstream instantaneous RCD trips.
Ah, so the fault is isolated locally and the rest of the board stays powered.
Exactly. It prevents unnecessary widespread outages. Very useful. Figure F15 shows this concept.
Okay. What about if equipment has its own earth connection?
Good point. Sometimes a particular piece of equipment, or maybe a group of equipment, might have its own separate earth electrode, perhaps for functional reasons, as shown in figure F16. In that case, fault protection is provided by an RCD specifically located at the circuit breaker for that equipment or group.
And its sensitivity.
Its sensitivity must be chosen based on the resistance of that specific earth electrode, using the same RA rules we discussed, by 50 RA or 25 RA.
Makes sense. One last TT scenario. What if, for some reason, metal parts aren't properly earthed? Maybe a broken wire.
That's where the additional protection from high-sensitivity RCDs really shines. In a situation where exposed metal parts might not be reliably connected to earth, maybe in very dry, rocky ground, or if a protective earth wire is damaged or disconnected, a standard fault protection RCD might not see enough current.
Right.
A high-sensitivity RCD, 30 mA or less, as depicted in figure F17, can still offer protection. It provides both fault protection, if the earth connection is poor but not totally gone, and crucially, that extra layer of defense against direct contact if someone accidentally touches a live part.
Okay, that gives us a really good picture of TT systems and why RCDs are absolutely paramount there. Now let's switch gears to the TN system. What's the fundamental difference in how this is set up compared to TT?
Right, the TN system. The key principle here is quite different. In a TN system, all the exposed metal parts of the electrical installation are